The last chapter, 16, concerned how we define temperature and heat and the effects that temperature and heat had on the expansion of substances, their change of phase, and the temperature. As we add more heat, the substance gets hotter and hotter. Continuing in this work we have on thermodynamics, we now look at the next chapter at how heat is transferred. In order to do that, we're going to look at this transfer first by conduction. It turns out that heat is transferred by three methods from one place to another: conduction, convection, and radiation. The first of these is by conduction, and we're generally familiar with what it means to conduct heat. Conducting heat, the heat is transferred through the material without motion of the material itself. Now that's very interesting. In other words, the energy moves from one place to another, the random energy, without the motion of any matter. And we need to think about that because that's very similar to how energy can be transferred from one place to another with waves. You recall that when we studied wave phenomena, a wave can carry energy from one place to another without actually moving the water or the sound itself. We need here to distinguish between what we think of as thermal conductors from thermal insulators. You obviously know what a conductor is. It's something like a metal, something that conducts heat very, very well. And an insulator is something that does not conduct heat well. It will be something that will keep you insulated. The formulas for conduction of heat in solids is really pretty simple, and it's of great importance. And here is that equation. And it's, as with most all of the equations we have, it is a linear equation in the pertinent concepts. So what we're going to imagine is that we have a substance. And this substance is going to have an area A, a cross-sectional area. It's going to have a length L. And we're going to put the two ends of this substance, this solid here, or whatever this substance is, we're going to put these two at two different temperatures, T2 and T1. And so there's going to be a temperature difference, delta T, which is equal to T2 minus T1. Now, it is reasonable to expect that the amount of heat that's going to go through this substance and be transferred from here to here is going to depend upon how much difference there is in temperature. If, in fact, T1 and T2 are equal, then there's not going to be any heat that's going to move from one place to another. But if we heat this up at one temperature and heat this up at a much higher temperature, then heat is going to flow back in this direction because the random thermal motion here is going to heat those molecules, hit them preferentially with higher speeds, make them hit the next molecules with higher speeds, all the way down as that heat is conducted, and the average kinetic energy or average random energy of the molecules increases all the way down as it's flowing. Well, you can see what the equation is. What we're interested in is the amount of heat that's transferred in a unit amount of time. Heat per time. Well, that's going to be proportional with some constant, the area. Well, why is it proportional to the area? Because if I had twice the area, I obviously would transfer twice the heat. So it has to be proportional to the area. But it's going to be inversely proportional to the length, because if the length is twice as great, only half the heat would flow down there. So it's going to be divided by L. And finally, it's going to be proportional to how much temperature difference we have, delta T, which is T2 minus T1. This is the critical equation that you have to remember for the conduction of heat. And remember, this constant here is called the thermal conductivity. K is called the thermal conductivity. Now, we can change this equation some. Of course, the thermal conductivity differs from one substance to another. We can change that equation in a very interesting way, because if we were to take the substance and divide the numerator and the denominator both by K, then we get an interesting new formula. We get the area times delta T divided by L over K. And that is A delta T divided by a new term called R, where R equals, by definition, the length of the substance divided by its thermal conductivity. That's a definition. And this is called the R factor. I can put it right here. And you find out about the R factor when you're using insulation in a home or you're doing any type of insulation. You're interested in this combination of things. What is the length, in other words, the thickness, if you wish, of the substance, divided by its conductivity. And you want a high R value if you want to insulate things. We're going to talk about that in just a moment. But the great thing about this is the R factors are additive. R factors are additive for building materials. And so if we have a wall and it has, say, sheetrock here, and then it has insulation and studs here, and then it has a board here, wood, maybe plywood, then it has bricks on the outside, then we want to figure out how much heat is moving through this wall, then we can take the R factor for the sheetrock, the R factor for the insulation, the R factor for the wood, and the R factor for the brick, and take these four things and add them together to get the R factor for the whole thing. 1 plus 2 plus R3 plus R4. And this R factor will apply to the whole system. If, on the other hand, you were to try to use this equation in its form, you would find that you would have to look at the temperature drop across each one of these substances, and the equation becomes extremely difficult to solve that way. So just remember that the R factors are additive. So I only have to worry about the area, the temperature, and what the total R factor is, and it's additive between the substances. Now let me tell you a little bit about R factors. First of all, with normal building materials in the United States, we use BTUs per hour for this. This is BTUs per hour. And those are the units that we want to use. And for this area, we're going to use square feet. And for this temperature difference, we use degrees Fahrenheit. Well, you could kind of guess that that's what we would do. And then we make the appropriate units in the R factor, this ratio of L to K, and then some values that we might want to look at are the following. The R factor for glass is 1. Then if it's double pane, the 2 pieces of glass, so you got 2. R factor is 11 for a 3.5-inch wall. So if you go to Lowe's or any of the building supply places and get 3.5-inch insulation to go in your walls, it's going to have an R value of 11. And it's going to fit into that wall stud. Now you may say, well, what, 3.5 inches? It turns out that walls are made of 2x4s. But a 2x4 doesn't measure 2 inches by 4 inches. A 2x4 measures 1.5 by 3.5. The rest of that got taken away in the sawing process. So in fact, the walls in all ordinary houses are 3.5 inches thick. So they make the insulation 3.5 inches thick in what are called bats. They're like blankets of insulation that roll out and exactly fill that 3.5 inches. And they have an R factor of 11. Now if I look at some other R factors, if I go to the ceiling or the floors, there I can put 6 inches in because I have a much larger, I have a 6 inches in those attic studs or the joists or the floor joists, so that gives me an R of 19. And you need to remember each one of these. The final thing you need to know is what about the wall before it's insulated? That is, I've got my sheetrock, I don't have any insulation, this is empty. Then I put some wood, then I put some brick or some siding on. What's the R value of a wall, or a ceiling, or a floor? The answer is all three of them have an R value of about 3.4. So that's all you really need to know. Before the insulation, you have an R of 3.4. This is R empty. And then with wall insulation, you're going to have, with wall insulation, an R of 11, and a floor about an R of 19. Floor or attic. Now what you can do is you can take your joists in your attic and you fill those with your insulation 6 inches. Then you can come back and put another set across these, and you got an R19 twice. And that's normally what is done today because energy prices are so high. We doubly insulate our ceilings because the attics get so very hot. Now, how do we actually solve a problem? Okay, let's look at a problem. This is section 17.1. So let's look at how we might solve a problem. What problems might you have on the test that utilize this equation? Well, there's our equation for heat flow. And remember, we're going to use the R values, which gives us this equation here. So delta Q, the heat flow per unit time, what's that going to be? BTUs per hour. We're going to be equal to the area, that's going to be in square feet, times the change in temperature, degrees Fahrenheit, divided by the R factor. Okay, well let's take a simple wall. Let's imagine that we have a wall here. It's a large room. It's going to be, let's say, 20 feet long. And the ceilings are going to be 8 feet high. So we know what this area is, and we're going to assume that this is a standard wall. So what would we have for the heat flow as we go in to out? And we're going to, let's say, we want our inside temperature to be 75, and the outside temperature is going to be 95. Okay, so we know what delta T is. Delta T is going to be 20 degrees. So our BTUs per hour, delta Q over delta T, is going to be our area. That's 20 by 8. That's the area of the wall. That's going to be 160 square feet. Multiplied by delta T, that's 20 degrees between the inside and the outside temperatures, divided by the R factor. And what's the R factor? It's 3.4 for an empty wall. That's uninsulated. So I'm going to leave this as a problem for you to solve this, and then compare this. This is the heat flow with no insulation. And I want you to compare that for a wall that is insulated. Now, we're going to compute that again. That would be delta Q over delta T. And that would have what? The same 160. The same 20 degrees, but now we've added an R11 to this. So the R factors add, so R11 and R3.4 are going to give us an R factor of 14.4. And now what I want you to do is to compare, this is yes insulation, and look at how much heat flows an hour that way compared to this one over here. And you can kind of roughly see what this is in your head. If I multiply this by 4, 3 and 4 is 12, then in fact this is going to have 1/4 of the amount of heat that flows up here. Let's see how close that is. 3.4, if I multiply it by 4, Yeah, it's going to be more than a difference of 4. It's very close. So this is going to be 4 times the heat flow. This is going to be 1/4 of the heat flow by putting the insulation in. So if you think about your bill, if you were to have in this one wall, if you lost $100 a month with your insulation, if you didn't have that insulation, it would cost you $400 a month just for the heat loss through that one wall. Well, now that we've done a wall, if we do a floor or a ceiling, it'd be very similar. So you could imagine a house that measures, say, 30 by 40. That would give you a square footage of 1,200, which is a reasonable but small, somewhat small house, square feet. And you would have normally the heat loss through the floor, through the ceiling, and through the walls. And so you'd have to compute the perimeter, and you'd compute the ceiling, and compute the floor. And I'm going to leave that to you as a homework problem to figure out what that is. And I want you to compare them with and without insulation. So when you compute this with the loss through the ceiling, remember you're going to compute with an R factor of 3.4. Then you're going to add 19 to it. And just do the same thing here. You're going to add 19. Now with your walls, if you go to a real cold climate, normally they will, if you go to the Dakotas, they will double the thickness of the wall. In other words, they'll put studs, and then every now and then they'll put the studs again here. So the wall will actually have 2 thicknesses, and they stagger these studs so that you have 3.5 inches here and 3.5 inches here, so you can get twice as much insulation. So instead of the walls being R11, the walls become R22. That's in the cold climate. You're not going to see that in the south very much, and you're not going to see it in older construction. But modern construction, when you're trying to save energy, it's worthwhile to build your wall twice as thick, and then you have half the heat loss there. But now there's something else that happens with a house. You don't have just solid walls with no windows. It's generally expected that windows will be 10% of the square footage. In other words, whatever your square footage is of your house, 10% of that is going to be in windows. So that means you're going to have 120 square feet out of your walls that are going to be windows. Well, what is your loss through your windows? Remember the R factor there? It's 1. That's horrible. That, that's 1/3 of no insulation at all, or worse than that. And certainly 1/14 of this. So you're going to have 14.4 times the heat flow through a window that you would have through your insulating wall. So windows are an extreme heat loss to homes, and therefore it's very important to try to fix that. One way you can fix it is add storm windows. Then you add one more and you get R is equal to 2. And if you have triple pane, then you can get R is equal to 3. Or if you have special types of gas in between 2 adjacent windows, then that can even increase it more, along with thermal reflectivity on the windows, which can also help you. You should be able to calculate this for floors, ceiling, walls, through glass, regular glass, and with storm windows, and answer a question like, how much would storm windows help this house?